Back to my course. We are dealing with the design and analysis of algorithms, and the first slide will probably be covering the fundamentals. At least this particular video will be covering the fundamentals of term analysis. And in doing that, we have to first of all consider now we want to deal with the input size. And when we're talking about input size, we're talking in relation to algorithms now. Usually we have algorithms with small we test it with small things like 20. Let's say we have a list of 20 people. When you're searching for the names of somebody, let's say from A to Z, now the person's name is Zacchaeus, and then it's just a list of 20 people. It's going to still be easy to eventually search and get to the end of 20 and find Zacchaeus there. But then what happens when it's 2.5 billion people? Then finding Zacchaeus in the long list of names, and then maybe Zacchaeus ZBD, for instance, where it's ZZ for the initials, you know that it's going to even take longer. So the input size usually is not dependent on the total number of elements that is inside the for the input for the algorithm. It could be, but we are not saying it is. And then how do we deal with that? We have to first of all understand the transversal and non-transversal algorithm. What are the transversal algorithms? Transversal algorithms are algorithms that every item in the input is reached at least once. In this case, let's say we are sorting now, everything has to be compared, and then because of that, every item is visited, and that makes it a traversal algorithm. For a non-traversal algorithm, it's not every item that is going to be reached, and in that case, we can have, let's say, a search for Zacchaeus ZBD. I don't know why I keep saying that, but if Zacchaeus is on the first, on the first, first on the list, is first on the list, it's going to be, it's going to be immediate, and then because of that, the input size is not very much dependent just on the amount of elements that are inside that input. So the traversal and non-traversal algorithms are the ones that cover that. Moving on, how do we now measure the running time of an algorithm? Usually we can say we want to deal with it in seconds, right? We can say, okay, since it's running time, why don't we just deal with standard units of measurements, which is seconds, milliseconds, and so on. The problem with this is that number one, it will depend on the speed of the computer or the computer being used. It will also depend on the quality of the program and compiler. And finally, it will depend it's very difficult to actually measure the clocking time of a computer. So clocking difficulty. Now for the speed of the computer, let's say you are using an old laptop, 2005 version, and then somebody is using a 2025 model. The speed of the computer for the 2005 will make an algorithm look slow, but then if you put that same algorithm in a modern computer of this age, it will be fast, and because of that, the duplicity of that makes it difficult to trust the standard measurement. We also have the quality of programs. When we are dealing with things like you use an interpreter to implement an algorithm, because the products of an interpreter they are usually slower than those made with compilers, because compilers are very good for production work, while interpreters are not so good. They are okay, but not as good as compilers. And then there are different kind of compilers, so you can expect that some compilers might do a better job than others. So finally, for the clocking, because of how fast that some programs will be run, we cannot actually measure the correct running time when it's given zero point 0.0 seconds as the running time of the computer of the algorithm. So we can't trust the standard measurements of seconds and minutes and milliseconds. What about counting all the operations and how many times they are being run in the algorithm? Like, okay, there's comparison, there's replacement, there's addition, there's multiplication, then you're accounting for all of those operations even in loops. Now let's say you have four loops going on. I don't mean four loops as in four. I mean four loops as in you have four for loops. Now when you have that, you are now having a bunch of operations going on inside them, and then you try to count all the basic all the operations, not the basic operation. You are trying to count all the operations. It might drive you crazy, and because of that you do not want to waste too much time with this guy, so we cannot trust this operation. So what we use and what helps us best, the basic operations on the other hand, they give us a very good basis for um, measuring the runtime, because they are the most important, at least in that particular algorithm. And then if they are being counted on a multiple of times, it becomes easier for us to know how fast the algorithm really is. And then what is the basic operation? Basic operation is the most important operation that contributes the most running time. So if others are contributing 2 seconds, 5 seconds, and this one is contributing 15 seconds, it's the basic operation. We should be focused on that because it's the one contributing the most to the running time. And where do these show up? You can have the basic operation being the stuff found in the innermost loop in the cases of sorting. So innermost loop, in the cases of sorting's basic operation will be the comparison. Yeah, it's comparing two things. Oh, is this one lesser? If it's lesser, move to the back. If it's greater, move to the front. Since it has to compare everything, the basic operation is the key comparison. But then what about mathematics, where we have plus, minus, star, and then this? What is the basic operation that will be considered here? Because this takes the most runtime to actually execute, this guy is the best candidate for a basic operation, then followed by this guy, and then these remaining two are not so valuable. So can it's it's just that we need to know that the one that contributes the most to the running time is what we will deal with as the basic operation. Now, how do we what when we're talking about theoretical analysis of time efficiency, what are we saying? We are saying we are trying to the time efficiency is determined by, or analyzed rather, by the determining the number of repetitions of the basic operation. Since we know now how valuable the basic operation is, we're saying how many times it is repeated is what we will use to measure the actual time efficiency, not seconds, not minutes, not milliseconds. We're going to be using the basic operations repeat time, like how many times was it repeated. We use that as the actual basis for calculating our runtime. And having said that, so let's say we have t is our running time here. T is running time. What is c of op? C of op is the uh, execution time of the basic operation. So the exec time of the basic operation. So is c of n? C of n is the number of times the basic operation should be executed. So what is the total, the approximate of the running time? It's going to be the C of OP, the product of C of OP and C of N. So that is for the running time. We have used that to calculate the running time. However, there are some drawbacks to this particular method. And what is the drawback? Number one, since we are dealing with basic operations for the algorithm, we are dealing with the innermost loop, or the thing that takes the most runtime. We are not giving enough credit to the other operations that are not basic. It's like the basic operation becomes the superhero, forgetting that then there are daily builders, daily cooks, daily other things that keep the entire city functioning. So by focusing too much on the basic operation, we are forgetting that there are some other important things to be considered. That's number one. Number two drawback is that the C of OP, which is the execution time of the basic operation, is an approximate. We do not is an estimate actually. We don't know what it is. We can't say for sure what it is, and we can't exactly defend its reliability like that. The count as well is also an estimate. All of these guys are estimates. We are estimating. We don't know exactly how fast how much time it will take for the basic operation to run. We don't know how much time the basic operation actually needs to run. But these have some benefits. Benefit number one, it helps us to uh, estimate reasonably the algorithm's running time. Because we know at least of the function of the input size. We know a little bit at least about the function of the input size. We know that the input size really affects how fast or how slow an algorithm will be. If the input size is big, we know that the algorithm will probably run slower. Let's say there's 1 million things to sort. It's going to be a lot slower than sorting 5 things, 6 things, 7 things. So the benefit is that it can at least give us a reasonable estimate of our of the running time. And then number two, it helps us to answer questions like ratio questions or relative questions. Like if I double the input size, how much faster will my computer will how much slower rather will the algorithm run? If I were to increase the speed of my computer by adding some extra GPU and CPU, how much faster will the program or the algorithm run? So that's the benefit for this. Okay. So we have an example, and we have this count, the count of our basic operation, and it's given as a function. C of n is half n into bracket n minus 1. And then what is the question? They said if we double the input size, how much longer will it take the algorithm? So we have this, and it looks very, very natural. Remember the formula we have: our T of n is equal to, or the estimate of it is C of OP and C of n, right? Having dealt with this, we can say that since we are creating we are doubling the input size, and we want to find out how long it will take, we are going to have a ratio thing to deal with here. So we will have the T of n and the T of 2n. So let's just create the ratio for them. And how do we do that? We just simply add this T of 2n and then we have T of 2n, and let's just clean this. Put an equal to T of 2n divided by T of n. So equal to the C of OP. The C of OP remains constant for the both of them because we are not exactly changing the execution time of the basic operation. We are simply just trying to double the input size and see how that affects our algorithm. Alright, so since we know that this is for C of n, what will C of 2n look like? C of 2n would note that this is a multiplication constant and it's not exactly affecting the content of this guy. So we have C of 2n looking like this. How? Okay, before I impute those values, let me try and simplify this. I should mention that the degree of the polynomial is the highest degree of the polynomial will determine the complexity of the function that we are dealing with. And then we have n minus, so I'll just expand this. We have half n squared minus half n. And since we are dealing with more of the highest degree, it's the highest degree that really matters, because if we start having big values for this degree here, it will make this one look insignificant. So we can just simply estimate and say half n squared, ignoring the other guys that come with. So we have half n squared for C of n. So C of 2n will now look, and you see that the reason why we did this is because we just want to make our calculations easier. Since we have the same eventually, since we care about something more than others, we should just try and conserve time and space. So putting 2n into this, we have 2n or square. So yes, in this place we should have 2n as well. So okay, C of 2n and C of n. Having done that, then we will have this going on. C of OP of half 2n or square and C of OP of n square. Now since these and these are the same, we can cross those off. This constant and this constant are exactly the same, so we cut them off. We'll be left with 2n or square and n square. And if we expand this, we have 4n square over n square. And since it's a ratio, we are trying to know how much faster. This and this don't exactly have much difference. So we know that the ratio of t 2n and tn is 4. So we are saying that if we double the input size, it will take 4 times as long to deal with it compared to before. So moving on, we have the best case, average case, and worst case time efficiency. How do we address this? For the worst case, we can determine the worst case of an input of size n as the input that causes the algorithm to run the longest among all possible inputs of size n. We are trying to say that whatever causes the most stress to the algorithm, that causes the biggest amount of time waste, or that takes the biggest amount of time for that algorithm, is going to be the worst case. That there's no other, it can't get any worse than that. That's the longest it will ever take. And it is very, very important because it creates an upper bound for our algorithm. We know that it will never pass beyond a certain boundary. That's why it's very important to at least have the knowledge of it. Worst case, the worst case time efficiency. What about the best case time efficiency? The best case time efficiency is not necessarily talking about the smallest input, like let's say 5 or 6, but it's talking about the input of size n for which the algorithm runs the fastest. It can be 1. Like let's even say that there's 100 people, but then because we are looking, maybe we are searching for a person, and then upon contact we already find the person, we can already say that that is the best case because we didn't exactly do anything, we just immediately contacted that. Since it takes the minimum amount of time, it's going to be the best case. And then what about the average case? Average case is just dealing with the typical input. It's talking about the random inputs, like for every other day apart from the worst case and the best case. um, what is the natural behavior of the algorithm, that is dealt with in the average case, not in the best case and the worst case. And note that the average case and the best case are the most important time efficiencies to note. The best case is, I mean, it kind of doesn't really do much. So having said that, we will now look deeper into the average case. Well, before we look into the average case, let's deal with the sequential search algorithm, because we need to make some assumptions if we are going to be talking about our um, average case. It's very, very intricate. And then, okay, since we have sequential search, what is the input of the sequential search? The input is an array of 0 to n minus 1 index, and then a search key k, and then the output is the index, not the element itself, the index of the first element in which a matches k. And then if there is no element, then -1. And when do you use -1 for an array? We're trying to escape from the array number 1, and we're trying to say that whatever it is not found in the array. If 0 is the first element, is the first index, then -1 is outside of the index of the array. So how does the algorithm look like? It has I equals to 0. Then when I is less than n, if a of the index I is not equal to, and then we are talking about the element now, if the element is not equal to the search key, then increment the value of I to the next index, and then continue doing that until this becomes false, or in this case until when ai is matching k. And if all of that works and does everything and still doesn't work out, then we can say return -1. So what is the worst case scenario? If we were to having to search through everything in the array, through the n items inside the array, then we can say that the worst case time efficiency dealing with this is n. Like it searches through the n elements, like all of the elements. Now what is the best case for the sequential search? The first item. This one search through all the items, that's why it's n. This one is searching through only the first item. You only search for the first item and found its result, so it's best case. Now what about the average case? The average case is given as n plus 1 divided by 2, and I'm going to get into that in another slide. Note that this n plus 1 divided by 2 is not us just taking these two values and dividing them by 2. It looks like it, but it's not. There's a whole lot going on inside, and we have to know that for the average case, we are dealing with random variables. We are dealing with random variables, and there's already something like that in statistics that we are going to come to. All right. So we are for the average case, we have to make some assumptions, especially with respect to the sequential search. Let's say we have in your exams, you are probably going to be given an algorithm that you are going to be doing the average case or the best worst case. Usually, nobody cares about the best case, but you are going to be given an algorithm that's trying to undo something, right? So now, for the assumptions for sequential search, we know that the probability of success is p, and then p can be 0 or p can be 1, but then we know the probability of success is p. Now, the probability of one of the elements matching key is the same for all, and let me explain that real quick with the dice. A die has 6 sides, right? So from 1 to 6, and then the probability of rolling face 1 of the die is 1 over 6. The probability of rolling 2 is 1 over 6, not over 6. The probability of rolling 3 is 1 over 6. So the same way, the probability of the first match of something is the same across board. There's nothing that is superior because algorithms are contiguous, which means that they follow each other from 0 to n minus 1, and they are also unique. They don't have um, like 0 0 1 1 2 2 3 4 4 4. They don't have that. They follow, and they are very 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 tight. So now the probability of the first match is p of n. We'll get into all of that with because of we are trying to okay, what happens when we find it, what happens when we find it, or what happens when we don't find it. We know that probability of success is p, and then we say p can be equal to 0 and p can be 1, but we know the probability of success is there. So probability of the first match out of everything is, this is for 1 over 6 for the die. We don't know the amount of numbers, so we are saying n. So p of n, that's the probability of the first match. And then in the ith position, that means let's say in the 6th or 7th positions, how many comparisons will have occurred? I. And in this case, we are just saying if we are already at the 7th element, it means that 7 comparisons had occurred. Now, if there is a case of an unsuccessful search that the search key is actually not even inside the area at all, the number of comparisons that will have been done is n. Why is that so? It's because it will search through everything, and then when it doesn't find anything, then it's just going to report back failure. And what is the probability of failure in statistics? Is 1 minus p naturally. They usually say q is equal to 1 minus p. So having said that, now let's look at the average case again, and then in this case we are now looking at the random variable ex, and then what is the value of that? We have the summation of xi pxi, so the value and the probability of the value showing up. So what will this look like naturally? It will look something like x1 px1 plus x2 px2 plus dot, 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 plus xn pxn. How does this now match with our average case? Since we said the average case is also dealing with the random variables, all the possibilities that can happen, we are going to have, since it's dealing with index of 0 to n minus 1, but it's actually just dealing with, okay, compares this, and then the next value, then the next value. So let's just say we're starting with 1. Okay, so if at this point, at point 1, p of n, like let's say on the first thing, p of n, because we are saying it's the same across board, and then this is the probability of success over the total number. Then we have again for point 2, or the second thing, we have p of n because it's the same all the way to n, which is the actual number of the thing itself, then dot p of n. We didn't use n minus 1, and we didn't use from 0 because it's going to be easier for us to do our summations with this rather than with 0 and n minus 1. So computing that, let me just make this more visible. Then we also have to consider for the probability of a successful search, which is n, then 1 minus p. So this is when the search is not successful. So we have 1, 2, all the way to n, and p of n. Now we can factor out p of n for all of these guys. So we have p into bracket, p of n rather, 1 plus 2 plus dot 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 plus n, then plus n into bracket 1 minus p. When you have this progression, this summation is equal to n into bracket n plus 1 divided by 2. Proof of that is, let's say we have this summation, I is equal to 0 all the way to 6. Then we can say 0, even if you had 0, it won't really do anything, right? So we're saying 6 plus, okay, let's say 1 plus 2 plus 3 plus 4 plus 5 plus 6. If we add all of these, we will have 21. Now putting this into this value, 6 in bracket 6 plus 1 divided by 2 is going to be 6 times 7 divided by 2, which is 42 divided by 2, and that is 21. And that here is the same as here, so we can really say that this works. Since we know now that this summation is equal to that value, you can simply substitute that and then have n plus 1 divided by 2 plus this guy over here, n1 minus p, right? So now this n is the same as this n anyway, since it's total number we are talking about. So this crosses out and we'll be left with p n plus 1 divided by 2 plus n1 minus p. So now what happens when p is actually not in it's a failure? In short, the search key is not actually inside their array. What will happen? We substitute 0 into the place of p, and then we have 0 n plus 1 divided by 2, then n 1 minus 0. So this all will be 0 plus n, so n. And when we have the search key not being present in the array, that's the worst case scenario. Worst case. Now what happens when there's actually that value, but we didn't say it is the number one, we didn't say it's the best case, but we know that at least the search key is there. Substituting 1 into these values, we'll have 1 in bracket 1 plus n over 2 plus n into bracket 1 minus 1. So this guy becomes 0, this guy becomes n plus 1 over 2. So this is how we get the average case. And I believe we can stop here for this particular video. Thank you for watching. I'll see you in another video.